All right, good afternoon. Year 2 engineering. All right, this is the next slide for the PDF I gave you already. I'm not going to read through everything, but I'm going to give a brief explanation of what is happening on this slide. Well, we're talking about DC biasing, and you know that DC biasing is when you add an external DC source. So DC signals are used for biasing. AC signals are usually amplified. So in an amplifier or in a circuit with a transistor, we use a DC just to bias, to turn on the transistor, but we normally amplified AC signals. So if you notice, if a music is playing, the speaker moves like this, boop, boop, ah. No, that's an AC signal going to the speaker. That is what we amplified. So we use DC to turn on the transistors. So the energy or power required to amplify the AC signal is obtained from the DC voltage, which is the bias and power supply. In all our transistor design in this class, the VBE, which is the voltage across the base and emitter junction, is 0.7, just like a transistor, like a diode. Alright? So we're saying now the DC current and voltages establish an operating point, which is the Q point, the crescent point, for stable operation. Q points are set within the active region. So when we say active region, remember when we look at the characteristic curve, realize that the characteristic curve has different regions, where in this section is referred to as the active region. Down this section is called the cut-off region, and here is the saturation region. So to bias, to make the transistor work, especially as an amplifier, we have to bias. The Q point has to fall somewhere within the active region. So here we have on this diagram, we have the Q point falling either at A, B, C, or D. Now, if we bias the transistor, as I said, Q point deals with load line, so we don't draw a load line, right? If the load line falls anywhere on these three sections, you have different results, and results are given here. So this result says if we bias it at A, is no bias. As you can see at point A, no voltage there, so there's no bias. But at point B, which is the second one, at point B, it allows a positive voltage and a negative voltage signal amplification, and it ensures linearity of wide range. So therefore, you can amplify, it's in the center, so it's clear you can amplify both negative and positive voltages, and it comes through clear without any distortion. Now if you take it to C and you amplify, you put the load line falls at C, you have a range of negative excursion would be limited or cut off, since it is close to the cutoff region. So this is C. So if the load line comes right here at C, right, and this is your Q point, then you find that it's so close to the cutoff region down here already that part of the negative section of the waveform, if you put a waveform, will be cut off. Because remember, so AC signal is an AC waveform, so you have the sine wave with drawn over it like that. If you do it in B, sine wave look like this. So the negative and positive side will come through nice, but at C, the positive part will be cut off because it's close to the cutoff region. Now, if you bias your transistor and the load line falls at D, which is your Q point is at D right here, you'll find that this is what will happen. A limited power amplification, since very close to the maximum power levels. So this section here is referred to as the maximum power level. The amplifier will not go any lower, that the transistor will not amplify any more than this PC max. So D is too close to the PC max, so you'll find that you will have a limited power amplification since it's very close. So it will not amplify as much as you will want. So that's it. I don't want to go more than 4.5 or 5 minutes. If you bias your transistor that the Q point falls at these areas, either A, B, C, or D, these will be the results that you have. You must know this by heart, and you should be able to say what will happen if you bias the transistor in any of these regions.